Did we just find Planet 9? There have been many predictions over the years of a giant planet wandering the extreme outer solar system, and there have been a number of good reasons why this might be true. There's been a bias in the distribution of the direction of the orbits of long period comets. There's been a strange distribution of orbits for the objects in the scattered disk. And when we run simulations of the early solar system, it's hard to make something that fits the distribution of the giant planets that we have. So there's even been a name suggested for this wandering giant planet, Tyche, the Greek goddess of fortune, the good sister of Nemesis. Some people have suggested that it might be 4 times the mass of Jupiter, orbit 15,000 astronomical units out from the sun. An AU is the Earth-Sun distance. So this is a quarter of a light year, and it would take 1.8 million years to go around the sun at that distance. This seems extremely difficult to rationalize as to how it might remain attached to the gravity of the sun if it was that far away due to passing stars. And of course, out that far, it would be cold with just a little bit of the heat of formation and the radioactivity within the body, keeping it above zero, above the temperature of outer space in general, but detectable by infrared, I would have thought. And others have suggested more sensible orbits, 500 astronomical units, 20,000 years, those sorts of numbers, much greater than any object that we've discovered to date. So the reasons for all of this are the long period comets that seem to come in from the Oort cloud, that hypothetical reservoir of icy bodies right out at the limit of the sun's influence that may get deflected inwards occasionally by gravitational interactions and fall inwards towards the inner solar system. And we see a lot of those. And there have been analysis in the past that suggest that perhaps they're not coming in at random, and that maybe there is something deflecting them that we haven't yet discovered, some massive extreme outer solar system body, maybe even a companion of the sun. Then we have the scattered disk, the orbits of the objects beyond the Kuiper cliff, beyond the end of the Kuiper belt, that second asteroid belt beyond Neptune, out beyond about 55 or 60 astronomical units. And the first object to be found out there was Sedna. And we can see these scale maps of the solar system from the inner to the outer solar system, then to Sedna's orbit, which is the big, long, thin elliptical orbit way out beyond Pluto, taking 11,400 years to complete one lap, and going out from a close approach at 76 AU, going all the way out to 937, nearly 1,000 Earth-Sun distances away. That's an enormous orbit. But Mike Brown from Caltech said of Sedna that it shouldn't really be there. He said there's no way to put Sedna where it is. It's never coming close enough to the sun, nor is it far enough away to be affected by passing stars. So it's a bit of a weird one, that one. And it has a number of companions, the sednoids, as they're now known. I've talked about those in other videos, but they all seem to be clustered with their long axis of their elliptical orbits over towards one side of the solar system, suggesting that something is marshalling them, this hypothetical Planet 9. So the third reason for all of this is the gas giants of the solar system. They probably formed by sweeping up material, and as they grew, they would spiral inwards due to friction. And in particular, Jupiter and Saturn got into a 1-to-2 orbital resonance fairly early on. They're now not in that pattern, they're in a 5-to-2 ratio now, but a 1-to-2 ratio was very unstable. And the simulation that is running on the right, which is repeating, begins with 5 giant planets in red dots there and simulates the motion around the event that happens after about 20 million years, is that In fact, one of the giant planets gets hurled out of the system. So there's 5. We start going, we run for a while, and then this happens. One of them gets kicked way out, and we end up with 4, and it disrupts a lot of the material in the Kuiper belt, rather, which may account for the late heavy bombardment of the planets of the inner solar system, with a lot of cratering that seems to have gone on about 3.8 billion years ago or so. So there are several reasons why there might be this 5th giant planet somewhere out in the extreme solar system. But we've looked and we haven't found anything up to now. The IRAS satellite infrared surveys of the 1980s looked around the whole sky. The 2MASS survey did the same in 1997 to 2001. And we've got the WISE spacecraft up there, another infrared explorer. And they found nothing. Well, they found things, but they're all more distant, out in the galaxy, as close as about 6 light years, but still nowhere near the solar system or the scattered disk, which is where we're really looking. In fact, they have ruled out pretty much anything of any significant size out to about 1,000 light years. Not 1,000 light years, 1,000 astronomical units, I beg your pardon. But the problem is that we've still got those issues with the sednoids and the long period comets, and perhaps even with our simulations. So what's this new result all about? Well, it's taken 2 surveys, the IRAS survey from the 1980s and the Japanese Akari survey from 2006 to 7. And with the 2 of these surveys, individually, they only spanned a few years each. And a moving object in the outer part of the solar system would not move very far in just a couple of years. But by comparing the 2, we have a 23-year-long baseline, and that's much more effective. So how far would an object out there move in 23 years? Well, let's make it easy. Let's start with a 23,000-year-long orbit, maybe at around about 500 astronomical units from the sun. This would manage to cover 1/1000th of its orbit in 23 years. Nice, easy calculation. And 1,000th of 360 degrees, well, that's 0.36 of a degree, 21 arc minutes. We would be able to detect that relatively easily. It's large enough to see without being so huge as to give us a problem. So all we have to do is look at the 2 surveys and compare all the readings. Now, the problem with that is that IRAS measured 350,000 sources and Akari 1.3 million. So you have to compare every one against every other one, potentially, if you're going to do this by brute force, and you end up with 455 billion comparisons. Now, even with a fast computer, that's going to take a while. Not impossible, but we probably should filter it down. So first of all, let's eliminate stationary objects. If there are only, we're looking at the objects that are present in one survey and missing in the other one, not in the same place, then we can eliminate all the things that don't appear to move. And that gives us a list of potential moving targets. But of course, they might be other things. They might be novas or distant supernovae flaring up. They might be passing asteroids from the asteroid belt much closer. And of course, if they just appear once in the image, then that's going to be a real problem. And they could be random events, cosmic ray strikes in the electronics, all sorts of things can cause a sudden dot in your data that is there one moment and gone the next. But we've already estimated that the movement should be of the order of 0.36 of a degree. So we could ignore anything too far apart. If we have 2 objects in our list of things that have appeared in one photograph and not in the other, and we compare them all against each other, well, we only have to worry about the ones that are relatively nearby, maybe between half of 0.36 and double 0.36. So that would cut it down dramatically. We can also only look at things that are of the same brightness. This is an image of a Kuiper belt object that's been circled there, and you can see there are many, many dots in the image. This could be a real problem trying to compare all of these, but you can pick ones that are of similar brightness between two positions, and then maybe get rid of an awful lot of the comparisons that you would have to worry about. We can also decide that we want to set a limit for how bright the target is likely to be. Are we looking for a really bright object or a really faint object or somewhere in between? And so we could choose a range of brightnesses and throw away things that are too bright or things that are too faint. But we have to kind of know the answer for that. And I have included here the discovery photograph from the discovery of Pluto, illustrated by the arrow there. And there are two frames, just part of the right-hand one is visible. But you can see it's supposed to be the same. And Pluto is present in one and gone in the other. But so are a lot of other objects that were, in fact, just background stars. So you could see that this could be a little bit difficult. So how many pairs of our potential 455 billion comparisons made it through all of those criteria, that giant set of filters to knock that number down? Well, the answer was 13, and that's much more manageable. Understatement, really, but there you go. So it was enough that visual inspection could be taken. We can have the human brain and the Mark I eyeball take a look at 13 potential pairs. And by doing that, the original authors of the paper that came up with this result eliminated 12 and just left one candidate that looked plausible. So what did they say about it? Well, it appeared to be about 500 astronomical units from the sun, and maybe somewhere in the range 7 to 17 Earth masses. So that's somewhere in the super Earth or sub-Neptune territory. Quite plausible, in fact. But of course, the filtering process was only going to let through candidates that were matching these criteria, because we'd already selected only those things that had moved about the right amount for 500 astronomical units, and only those things that would have been around about the right brightness for that distance. Are there any issues with this? Well, it's only a pair of observations. The picture on the right is the discovery image for Albion 1992 QB1 by Dave Jewett and Jane Liu in Hawaii, the first Kuiper belt object to be discovered after Pluto. And there are three detection images here, spaced across different dates, and the object has moved between the three of them, and the distance it's moved seems to be in agreement with a moving object along an orbit. And three observations is so much better and more convincing than just two. First of all, there are 3 factorial ways of arranging three things. So you've got a 1 in 6 chance of them being aligned like this, rather than if there are only 2, where your chances are 2 factorial, which is 2. So you're 3 times better off with 3 objects than 2. And if the speeds match as well, then you've got a whole extra constraint. So I think that's much more convincing. And in the case of Kepler and discovering exoplanets, something which I know something about, then you really need to find 3 transit events in order to prove that you have a proper transit, rather than just a couple of random events that look similar. The distance, the time between those transits being equal is a crucial factor. So I would be more convinced if we were to find a third event, a third image, and be able to line those things up. And the other problem is that with all of those possible sources and all those 500 billion pairs, 455 billion pairs of possible lineups that you had in the original data set, the chance of finding that you have a couple of objects of roughly equal brightness fairly close together somewhere in the data has to be fairly significant. Somebody who's good at statistics could probably do the maths on that, and they would, I think, come out with the fact that it's quite likely that you might find a false positive for a couple of randomly moving asteroids much closer to us, or a distant nova, perhaps one of each, who knows? There are many ways in which you might find one object out of that many pairs. So what do I think is the answer? Well, I do hope that this turns out to be correct, but these sorts of tentative results don't often get confirmed, so I wouldn't get my hopes up. And I would caution you with the discovery of Vulcan, when the hypothetical Vulcan planet moved across in front of the sun. Dr. Lescarbot spotted a moving object, and he'd already read the letter published by Leverrier suggesting that such an object might be present. So he was already inclined to believe it. And of course, Leverrier, when he went to inspect Lescarbot's observatory and try and prove that this was true, was doing exactly that. He was confirming that his theory was true rather than trying to prove it false. And so you have to be a little careful here. So what do we need to do? We have to follow up. And I would say that's exactly what the original authors of the paper had to say. They're not claiming a discovery, they're just claiming an intriguing possibility. One of the things I love about astronomy is that we just don't know, something that Sir Patrick Moore used to say on many occasions. And I'm very, very interested to see what happens to this story as we go forward. So thanks very much for listening, and I hope you found that interesting. Bye for now.